just keep in mind that I have 200 students altogether, okay? Okay, so let's start the class. I just want to make sure I didn't say something wrong last time, so that way we can also review. You need to know how to use your right hand. So again, you're going to have a lot of conceptual questions. So in this case, remember that when you see dot, people got confused. When you see dot, the magnetic field is coming towards you exactly because it's like an arrow. Okay, you see the point. You don't see the tail. When you see crosses, it means it's going into the screen. So how do we deal with this? So you have your right hand. So the velocity is in this direction. The magnetic field is, so you have to rotate. You have to do one finger at a time. So velocity is going in this direction. Magnetic field is towards you. So the force is down. Okay. So you see the velocity and the magnetic field are in the same plane. If they are parallel or anti-parallel, there is no force. The magnetic field here will produce a centripetal force, so it make the isotopes curve. Inside here, it's called the velocity selector. You are applying both a magnetic field and electric field. So the electric field is down. What about the force from the electric field is down? What about the magnetic field? You see the velocity is this way. Magnetic field is in the screen. So the force will be up. So you manage in that case to have the electric field exactly, the magnetic force exactly equals to the electric force. So that's why you keep only the isotopes with the same velocity. So what will tell them apart will be only their mass. Okay, so that way we can count how many isotopes, we can find the mass of isotopes, and so forth and so on. So I wanted to go back to that to make sure. Also for the test number 3, I recommend that you see those chapters, you have 3.1, 3.2 to review. Okay, is that right? 3.1, 3.2. At the end of these units here, you have equations that I took from the book Johnson and Cutnell at the end of the chapter. So I recommend to print them out because you have all the equations, but you also have the explanation, so you don't get confused which one to use. Okay, 3.1, it's not there, but at the end of 3.1, it was the first unit of magnetism. You also have all of those equations, so you don't get mixed up. I also recommend to have open when you do the test these slides, big ideas, because you have all the, I try to summarize everything. Okay, so Ampere's law, these are the equations we have used here. And you see here when you have two wires and they are parallel to each other, if the current is going in the same direction, they're going to attract each other. If the current is going opposite direction, they're going to repel each other. Okay, so that will be the equation at the center of the loop. And that will be the equation if you have a straight wire at a distance r from the wire, that will be the magnetic field. The magnetic field like to curve. Okay, and we started with induction. So that's the last unit of magnetism. So I want to review that. We called the flux, the magnetic flux. So the unit, it's going to be Weber. Okay, so you can think of the magnetic flux as the number of field lines poking through an area A. Okay, so you make your own area like this one. So that will be the area A. It's like an imaginary area. And you can see that you have field lines poking through. So imagine it's like water flowing from this area. We define this flux, okay, as the magnetic field, Okay, the magnitude of the magnetic field, because of course, if you have a stronger magnetic field, you're going to use those lines to show that. If you have a stronger magnetic field, it means that the lines will be more packed together. Is that clear? It's a contour line. So it depends, of course, of these, how many lines are going to poke through, how strong is the magnetic field. It depends on the area, obviously. If you take a smaller area, you're not going to catch as many lines. If you have a large area, you're going to catch more lines. And also it depends on the orientation of the area relative to B. So in that case, you see B is perpendicular to A, okay? So that will give us the maximum flux. So the magnetic flux will be the magnitude of B, the magnetic field, times the area. That angle here will be the angle between this vector here and that vector, which is 0. So cos 0 will be 1. But you can see here, what's going on here? Are you catching any field lines in your little net of area A? Imagine it's like water flowing and you have little shrimp or plankton, going with the flow. And are you catching any plankton, right, in your net? No, right? Nothing will be caught inside your net. So that means the flux is going to be 0. Is that clear? So now you have like a conductor. Okay, so this is a conductor, so it's a loop, like made of copper, for example. So let's say you have a closed loop, okay, and there is no current flowing through that loop. So you can imagine you can attach like here an area, it's like a phantom area. And you see here, is the flux positive in that case? Is there a magnetic flux? Yes, you see those lines are poking through this imaginary area that you have attached to your conductive loop. Is that clear? So you take a loop, imagine I have a wire in my hand, I make a loop, a closed loop, okay? And you see this is the area of the loop, okay? So I touch imaginary loop, and you see you can count how many lines are poking through here. So that will be the magnetic flux. The magnetic flux is maximum. The magnetic flux here is going to decrease or increase from here to there. Decrease, very good. Okay. So if you have like those little shrimps being carried by the water, you're going to catch less. The flux will be equals to B times A times cosine of the angle. So the angle will be by how much this has been spin over. Okay, so if this is 45 degrees, that means the flux will be B, A times cosine 45. So it will be less than B times A. Is that clear? So the flux is decreasing. How much is the flux here? 0, very good. Okay, and then it keeps spinning. So from here to there, the magnetic flux is gonna increase again in magnitude, okay? And here again, it's gonna be positive, maximum in magnitude, except it's negative because see, orientation is this way, magnetic field is that way, so the flux will be negative. My point is that as long as the number of lines poking through the area is changing, you're going to induce an EMF. You're going to induce a current. So this is called the AC generator, because doing so, the current is going to flow in one direction and then it's going to flow in the opposite direction. So this is how we produce electricity today. Okay, so this is called the EMF, right? You are inducing EMF. Yes.
I have two questions. So for the first side where it's decreasing,
So here it's positive because you see you decide that will be your orientation for orienting the area. So you attach a little vector like this, and if the flux go with this little vector, it's going to be positive. So the flux is positive, here it goes to 0, and here it's going to be negative. Okay, because that means the cosine of this angle here, okay, it has spin by that angle, the cosine is going to be negative. Okay, although it's more advanced, you don't have to worry about it. But the thing to understand is that in that case, again, the flux is going to be maximum, even though it's going to be negative. Yeah. So yes, so you see A is in this direction, B is in that direction. So that means you have an angle of 90 degree, cosine 90 equals 0. Okay, so this is the definition of flux. You have to imagine like the flux will be the number of field lines poking through an area, okay, a net, like a net that you use to catch fish, okay. The number of field lines will depend how strong is B, because B is very strong, you're gonna have more field lines, and it depends on the area. And of course, it depends also on the orientation, okay. So this is called the AC generator. So let's see, I have found a new app. It's not a new app, but it's in my stuff, so I have to dig. Okay, so this is how it works. This is how we produce AC. So maximum flux, 0, and then it's increasing again, and then it's going to be 0, and it's going to increase again. So doing so, you are inducing a current inside the loop. Okay, so you are inducing a voltage, which is called the induced EMF, and that's how we produce AC from the outlet. Is that clear? So you see the current will flow in one direction, and then it wants to flow, oops, do you see that? In the opposite direction. I will tell you why it has to change constantly direction. See how it works? Is that clear? But you need, it's not like you are getting energy for free, okay? This magnetic field is a way to transfer energy from mechanical energy, because you have to spin, okay, you have to do work, to electrical energy. So in the real world, in a electric power plant, electric power plant, you need like some turbine here, and you want that to spin. And the way you do it, you are using, for example, water steam. Okay, and how do you get water steam? You need to burn something. So you burn gas, natural gas. You burn oil. You can burn nukes like uranium. Okay, so you boil water. Water turn into steam, and the steam will make that turbine spin. Okay, and that will then you can convert mechanical energy into electrical energy. Is that clear? So you need to spin here, otherwise it's not going to work. Now what you see here is called the peak voltage. And remember, the peak voltage that we get here from the outlet, okay, is not the same as the 120 volt that I'm going to measure with my voltmeter. 120 volt is square root of 2. The peak voltage is 120 times the square root of 2. Okay, remember that? We already talked about that. So I'm going to review, but let's make it spin faster. Now, you see when you spin faster, do you see the voltage? Does it increase or decrease? The peak voltage. Increase, okay? You're gonna because you are spinning faster, so you have more energy input, so you're going to have more energy output. Now, if I spin slower, you see the frequency decreases, okay? But the peak value for the voltage also decreases. Okay, so whatever you put in here, you will get out. Now, the thing to understand is that the rate at which it's spinning will be, in our case here, 60 cycles per second. So it means in the power plant, that loop here is going to make 60 revolutions in 1 second. So the frequency is 60 hertz. So that's why when you use an oscilloscope, for example, to look at the voltage that you have here, it's going to do plus, minus, plus, minus, plus, minus like this, 60 times a second, that will be 60 hertz. Okay, so that's how it works. Now, something interesting. I might want to, okay, so so we already have discussed that. The equation for the EMF induced will be equals to the number of loop times the rate at which the flux is changing. Okay, so for example, if you have like a solenoid here, there is no current whatsoever, and I start to take a magnet in and out, you see, you can attach here a imaginary area, and the number of field lines poking through is going to change. Because of that, you're going to have an induced EMF. Okay? That's one way to do it. And we already work with that equation here. The change in flux will be equals to, so B, the magnetic field after times area after minus magnetic field before times area before. So we already talk about it. The unit will be volt. Is that clear so far? I want to talk, and that will be a nice review. I want to talk about something called Land's law. Land's law is about conservation of energy. You cannot have anything for free, right? So it means if you want to produce electricity, you need to put the oomph into it, right? It cannot happen like this. You need to put the energy in. So that's why. So in that case, okay, so it's rotating. So you're going to induce a current. The question is which way the current is going to flow. It's going to flow in such a way that it will oppose whatever gave rise to. I explain. So this is here a magnetic field, yes? So let's review for the test. Which way is the north? So the magnetic field always goes from north to south. Very good, okay? So somewhere here I have a north and somewhere here I have a south. So this is north. This side will be north. So you see the induced current is gonna flow in such a way that will oppose whatever gave rise to. So you see the induced current is going this way. Do you agree? So the other side will be what? That means this side will be what once it's induced? Let's review. You have a current flowing in this direction, remember? So you do that with your hand. That will be the current. That's going to be what? The north, right? And that will be the south. So a loop of current will behave like a bar magnet. That will be the north and that will be the south. So the current will flow in such a way that it will oppose the magnetic field that gave rise to it. So it will flow this way, so it's going to show the south to the north, right? Well, it's not on the test, this Land's law, and we'll get back to that today. So just to give you an idea how it works. And you see now it's flowing in the opposite direction. So the last one, let's review for test 3. Last picture here, you see it's flowing in this direction. So do you see that's going to be the north over there? And that will be the south? Okay, so for this one, that side here will be the north, and this side here will be the south. So we'll explain after why. Okay, so for now we're going to focus on that, how to produce AC. Okay, so you see if you have a loop here, so it's a conductor and it's rotating inside a magnetic field, you're going to produce a AC voltage, say with a peak voltage. So let's go back to the slide. Let's see. By the way, for this one too, at the very end here, at the very end of the unit here, you have all the equations. Okay, this is not on the test, okay, but it will be mostly for the final. But you have all the equation with the explanation, so maybe you want to print this out. Okay, so let's go straight to the equation. When you have a loop of it's not a loop of current, it's just a conductor that's going to spin inside a magnetic field. You're going to induce an EMF. That will be the final equation for the EMF here. Okay, it's going to be the number of loop times the magnetic field times the area, and that will be the speed at which it's spinning. Okay, this is called the omega here. So let's review physics 1 just a tiny bit. So remember in physics 1, you used to have like delta x. Okay, so that will be a displacement equals the speed times the time, right? So that was for a linear speed. So displacement is in meter, the speed is in meter per second, that will be in second. Likewise, when something is spinning about an axis, you can define, you can find the rotational speed, okay? So it's called the rotational speed or the angular speed. It's going to be called omega. Okay, so omega will be equals to the angle in rad divided by the time it takes. Okay, so that will be in 1 second, what's going to be the angle that will be covered, right? So for example, if you have 3 revolution per second, that's also a rotational speed. Okay, so the unit is revolution per second. So how can I convert that in radian? 1 revolution is 2 pi. So I can do 3 times 2 pi in 1 second. Okay, so that will be about 6 pi rad per second. So that will be a rotational speed. Okay, it just tells you, it's just giving you revolution per second. Okay, so if I have, for example, 60 revolution per second, that will be a frequency of 60 hertz. Okay, now what we call, so that will be like a frequency 60 hertz. Okay, so that's what you get from the outlet. What's going to be the period? Remember we talked about that. So the period will be the time for 1 cycle. So 1 over 60. Is that clear? You have 60 revolution in 1 second. Okay, so how many seconds for 1 revolution? It's going to be 1 over 60, which is 0 0.06 something, 117 second, okay, per cycle. And this is called the period. So that is to say that in your power plant, the loop, okay, is making 60 revolutions per second. I'm going to produce a AC voltage and the frequency will be the same. Okay, so it means that I will get at the end, okay, AC voltage going up and down and up and up and down. That will be the time here. That will be the voltage. The peak here is going to be about 170 volt. The RMS here will be 120 volt AC. And the period here is 0.017 second. So that will be the AC voltage that you get from the outlet. So it's like a review. Is that clear? Okay, so I don't know if I have a app here. I try to make everything in a nutshell, so it's not too so you see here it's rotating, and you can find how long it takes to go one revolution. So it goes down, no, 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 stop. So it takes about 3.6 seconds to go around. Can you find omega in that case? The times for one revolution is 3.6 seconds for one cycle. So omega will be, how much is a revolution in radian? 2 pi. Okay, so it goes one revolution. One revolution is 360 degrees, is 2 pi divided by 3.6. So that's going to be 1.75 rad per second. So in my cute example here, that will be the rotational speed, okay, in rad per second. You see that the frequency, okay, you see it's going to be one revolution in 3.6 seconds. Okay, so that's going to be the period. So what's going to be the frequency? 1 over 3.6, so it's going to be 0.2 hertz. Okay, so the frequency is how many revolutions per second. The period is how long for one revolution. Is that clear? So all that just to tell you that to produce the AC that we get here from the outlet, we're going to have like a rotor. So it's something that will spin and it will make, okay, one revolution in 0.017 seconds or 60 revolutions per second. And at the end, the EMF induced, it's going to be that expression here. Omega t is going to be the angle here between your magnetic field here and the loop, okay, by which it has been spinning. So that will be your angle here. Is that clear? So we're going to take an example that will be easier. So again, each time you have something that will rotate, it will induce an EMF, so it will induce a current, and that will be the EMF induced, okay? It's a sine because it's going to go up and then down and up and down. That expression here for the EMF, that will be the peak EMF, okay? So the peak EMF depends on what? What is N? Number of loops, very good. What is A? The area attached to the loop that is spinning. What is B? The magnetic field in which the loop is spinning. And omega will be the the rotational speed, right? How fast it's spinning. If you make it spin faster, the voltage will increase. So great pop quiz questions here, okay? As you increase the speed at which it's rotating, the voltage is going to increase. If you increase B, the voltage is going to increase. If you increase the loop here, okay, the voltage is going to increase. If you increase the number of loop, the voltage induced is going to increase. That expression here is just to tell you that it's going to be like a sine function. The voltage is going to be positive, 0, negative, 0, and so forth and so on. Is that clear? Okay, so it means if you look at the outlet that we get, so if I ask you a question for the final, if you look at the outlet here, what's the frequency? 60 hertz, right? So 60 revolution in 1 second. Do you remember? So if you look at the outlet, you see you have the hot here and you have a return path, and here you have the ground. That means the outlet will be plus, minus, and then this one will be minus, and then this will be plus, and then this one will be plus, and this one will be minus. It takes about 0.017 seconds for that to happen. Okay? Because it's a AC voltage. Is that clear? So what's the peak voltage here that we have about? It's going to be 170 volt. But the RMS, remember, it's going to be 120 volt. 120 volt, 170 volt. And you remember how do you go from one to the other one? You multiply by the square root of 2, about. Okay, so V RMS equals V peak over square root of 2. Is that clear? Okay, so again, I can show you an app. I try to make it as easy as possible. It's not easy, okay? This unit is not easy. Okay, so you're using here some kind of mechanical energy. You make that loop here, so it's a closed loop, it's a conductor spin inside a magnetic field. You're gonna so this is a resistance. You're gonna induce a AC voltage. Okay, the peak voltage depends on what? Remember, it depends on how strong is a magnetic field. Yes, because if it's stronger, you're going to have more feed lines. Second, it depends on area. Very good. Third, it depends on rotational speed. Very good. And also the number of loops. Okay, you don't just take one loop. You're going to have many, many loops. So that's how it works, right? And the sine is just to show you that it's going to make a sine function there. Okay, I will help you for the pop quiz also. See, you have the same thing here. So this is going to oscillate, okay, 60 times. So 60 back and forth, 60 times per second. It will have the same frequency as the loop that is rotating. So you are inducing AC voltage, you are inducing AC current. Same thing here. Is that clear? Why does it have like a... Oh, that's... Okay, so help each other, talk to each other, and try to do this one. So don't stare, okay? We're going to use that equation here. Okay, so you have a coil on the AC generator. So that's going to be the frequency. Okay, so 60 hertz. So omega, okay, remember omega, okay, that's the speed at which your coil is spinning. It's going to be 2 pi, because that's one revolution, over the period. Okay, so how long it takes to go one revolution, which is the same thing as 2 pi times the frequency. Okay, because 1 over the period equals 2 pi equals the frequency. Is that clear? So omega has to be in rad per second. So how many revolutions per second? The revolution has to be in 2 pi. Do you understand that? Okay, so it's like a speed. It's going to be the number of revolution in radians divided by the time elapsed. So you have this equation there. So you have the EMF induced. So that will be EMF, but it's the RMS value. Okay, so you can find the peak value, which is 120 times square root of 2. Okay, so now you can do it. It's not an easy chapter, so if remember to read the book AC. AC. So what's the equation? EMF induced will be equals to the number of loop, okay, times the magnetic field, okay, times the area, okay, times the speed, okay, times, and that will be just my sine. That will be called the peak value. Sine or cosine, it doesn't matter, okay? You can have a sine or a cosine. Okay, and we do have the peak value. The number of loop is what? 500. We have the area. We have the speed, omega. Omega is 2 pi over the period. Okay, and the period is 1 over the frequency. So you can use that equation here. And you want to find B. You're doing it? You plug it in, right? So the EMF, the peak value, it's going to be 170, right? So 170 equals the number of loop is 500. The magnetic field is, I don't know, because that's what we want, times the area is 3 times 10 to the negative 3, times the speed is revolution in radians. So one revolution is 2 pi over the period, and the period is 1 over the frequency. So it's going to be 2 pi times 60. So what do you get? So 170 enter, divide by 500 enter, divide by 2 enter, divide by pi enter, divide by 60 enter, and divide by this enter. So what do you get? Anyone? Huh? What do you get? 0.3. Did you all get 0.3? You sure? No, no, no. Yes, yes, yes. So you do 170, enter, divide by 500, enter, divide by, open the parenthesis, 0.003, enter, divide by 2 pi, in parenthesis, enter, divide by 60. Yes? Yeah. So the rotational speed, again, the rotational speed equals to 1 revolution and the time it takes for 1 revolution. Okay, so that's going to be the angle swept divided by the time it takes to sweep this angle out. The unit is rad per second. Okay, that will be the period because that's the time for 1 revolution. So you have the angle at a given time equals omega t. Okay, so that's just, it's easy to understand revolution per second. How many revolution per second? Except it's in rad per second. Is that clear? Now, you see here in this expression, back there, you see I have omega t. Omega t will be the angle swept between here and there. That will be your angle here. That will be your omega t at a given time. So just a quick review from, I think we did that already, from the unit AC. Let's go to Wolfram alpha. Because that's going to be on the pop quiz. So if you do plot, okay, phi, for example, times sine, inside here you always 2 pi, always 2 pi. 2 pi times, that will be your time, for example, that will be variable, divided by, and here we're going to divide by the period. So I don't know, I'm going to take a period of 0.5 for x between 0 and, I don't know, 3, for example. Let's see what we get. You see, you get a sine function. The period goes from peak to peak, or from here, so that will be 1 cycle. What's going to be the period here? 0.5. You always have it here at the denominator because 2 pi divided by 0.5, that's going to be your speed, okay? Revolution per second. So 1 revolution in radian divided by the time it takes, 0.5 seconds. So each time you have a sine function, you always have inside here 2 pi divided by the period. So let me ask you something. What's going to be the frequency in that case? If the period is 0.5, the frequency is going to be, if you have 0.5 revolution in 1 second, or 0.5 cycle, half of a cycle for 1 second. So how long for 2? Okay, 1 over 0.5 is 2. Okay, so proof, give me proof. You see the time here, it's going to be, so the time for 1 second, so you have 1 second. How many revolutions do you have? 1 cycle here, and then 2 cycle. You have 2 cycle per 1 second. So that means the frequency is 2 hertz. What's going to be the period? It's going to be 0.5. What's going to be the frequency? It's going to be 2. How do you go from frequency to period? You take the reciprocal. Okay? What's the peak here? What's the peak value? Yeah, so 1, 2, and 3, and 4, and 5. You see, you have the peak value here. So with a sine function, the coefficient here is always the peak value. At the denominator, you always have the period. Can I write this instead? I can put times 2. You get the same thing, okay? Because 1 over 0.5, it's going to be 2. Let's see. You see, you're going to get the same thing. 2 is your frequency. Do you see how it works? So from our AC, what's the peak value from the outlet? I love those type of questions for the final, by the way. What's the peak value? One, what? 120 is the RMS. 170, 2 pi x. What's going to be the period? 0.0, I forgot. 17, something like this. Are you sure? Yes? 1 over 60. And here we're going to put between. So you see the period is going to be 0.017. And if you count how many in 1 second, you're going to have 60. So you see, you always need math. It's not like even though you pass this class, it's going to be over, right? You are all science majors, so you all need math. You all need to understand that. So in 1 second, you see it's going to have 60 revolution. 60 revolution. Do you see that? And that will be the period. That will be the peak value. Okay, is that clear? So you all survive. You will all survive the pop quiz. Okay, so we get back to this equation here. The EMF induced will be equals to the number of loops, the strength of the magnetic field, the area, 2 pi over T, or 2 pi times F, so how fast it's spinning, and how fast the voltage is going to change, and then you have your sine here. So we did this one. So the answer indeed is going to be 0.3 Tesla. And they tell you this here it's going to be the peak value. The peak value equals to the RMS times square root of 2. Okay, so this is just to summarize everything. Okay, how can we induce an EMF? You can change the magnetic field. Okay, so that will change the number of lines poking through the area. Or you can change the area, okay, that will work too, because it's going to be more field lines poking through, less field line. Or you can rotate the conductor. So in that case, that's going to be the induced EMF. In that case, if you are changing the area, you see that the induced area, EMF will be that expression here. So that will be the rate at which the area is changing over time. And if you are changing the magnetic field strength, that's going to be the EMF. Okay, it depends on how fast the magnetic field is changing. So I try to summarize everything. Is that clear? Okay, next unit is going to be easier. This is the hardest unit, I think, conceptually. So let's go back to Michael Faraday. When he did his experiment, he did it this way. Okay, so it had like this is called a torroid. Okay, so I will show you what it looks like. It's like a donut and it's made of soft iron, for example. He had to insulate it. So at the time they didn't have plastic, so they used fabric. Okay, and you see they are not connected. These wires here are not connected to those wires. And he find out that so here you have a power supply and here you don't. When he closed the switch, when you close the switch, the magnetic field here expanded, was trapped inside the donut, and will induce an EMF on the other side. So that's the idea behind the transformer. And that was done by Michael Faraday. So let me show you. I have an app. I don't know what my things don't want to open. Oh, shit. Okay, so you see here you have soft iron, for example. The loop here, your circuit here is not connected to them. But when you're going to close the switch, the magnetic field is going to expand. Okay, the magnetic field will increase, but it will be trapped inside the donut. So the magnetic field lines are going to poke through this area, and it's going to induce an EMF there. So you close the switch, boom. Do you see that? And then nothing happens because the magnetic field lines will not change. Open the switch, you close the switch. So that was the original experiment done by Michael Faraday. And why is that so important today? And I'm gonna try to make demo. Okay, I cannot guarantee it's gonna work. That's the problem with demo. No, I like this one better. So you see here, this is a transformer. So let's say it's made of soft iron, and here you have a circuit. That circuit is connected to AC power supply. So that means the magnetic field here produced, okay, remember, you can use that right hand. So the current is gonna wrap around the coil. So the magnetic field is gonna expand and then collapse, expand in other direction, and then collapse, expand in other direction, collapse, and so forth and so on. So on the other side here, you have another circuit with no power supply, just the load. Okay, you see those magnetic field lines that expand, collapse, expand, collapse, expand, poke through this area. Okay, so it's going to induce an EMF. So today, this is the technology that we need. If you want, for example, my computer here use 20 volt, but this is 120 volt. So in this charger that I have here, it's like a transformer that will step down 120 volt to 20 volt. Okay, and you use this technology. So I will explain more, but that's the idea. Okay, I can show you that here. Here I have another one. You see here it's AC power supply. So the magnetic field will expand, collapse, expand in other directions. Magnetic field going this way, this way, that way. So on the other side, it's going to induce an EMF there. Okay? Is that clear? And that was found by Michael Faraday himself. Okay, remember? Didn't go to college, went barely to school until he was 12 years old, and nevertheless he was a genius, right? So he's the one who understood about 11 years after Oersted experiment how to produce electricity using magnetism. Smart, right? He was very good at doing experiment. That's how he did it. That's how we can produce electricity using magnetism. So I'm going to try to show you some demo. I don't know if it's going to work. Okay. Let's see if you can see. Do you see my little donut here? Okay, it's like soft iron. Okay, do you see those two circuits are not connecting to each other? This is called a step-up transformer. So if here I have 10 times the number of loops compared to here, I'm going to step up the voltage by a factor of 10 volts. So I'm going to try to do what Michael Faraday did. So here, okay, I have a power supply, which is here. So that's my power supply. On that side, need that to make it right. Okay, so this is what goes to the power supply, right? So on that side, I'm going to apply a voltage, okay? My goal is to show you that when I close the switch, I'm going to induce an EMF on the other side. I don't know if you can see well. So let's see, 20 volt. There is nothing here. Can you see there is nothing? Barely. I don't know why there is something. It's not supposed to be anything. Okay, so now I'm gonna plug that here, okay, and I'm gonna close the switch. Ready? Oops. Ah, when I close the switch, do you see the EMF? It's gonna be very small, right? Let's see if I have any current. Oh, a little bit, milliamps, very small, right? It's not very convincing, but it's the idea. I'm going to show you another video because today nothing works. The other thing I wanted to show you is that this is what transformer look like. If you are in computers, you have those little transformer here. Okay, so one side here, it's going to be 120 volt. I can connect that to the outlet. And on the other side, between the black and the yellow, it should be 6 volt, but it should be AC. Okay, so this is called a transformer. So I don't know if it's going to work or I'm going to electrocute myself. It's very possible that you're not going to have a test 3 will be your last test with me, right? So let's see. I'm going to go in AC. Okay, so I'm going to connect that here. Okay, so there is nothing here. Do you agree? Okay, no. So now I'm going to plug that. That will be 120. Do you agree? Okay. That. Ah, that works. Do you see? It's about 6 volt AC. So I step down 120 to 6 volt AC. So that's how your charger works, right? Because you don't want 120 for your laptop or your tablet. So this is a transformer. Oh, I'm kind of scared. So now I'm going to do between yellow and yellow. So yellow and yellow, do you see how much you get? About 14 volt AC. Okay, so this is called a step down transformer. Now, what I would like you to show you, if it works again, I have a mini oscilloscope. Let's see if it works. Oh, plus I'm like blind. So, ooh, it works. Ah, It's very, I don't know if you can see. Can you see? Okay, that's what you get here. So that's just to show you that this AC voltage is going to follow a sine wave. And can you see the frequency here? It says 6059.9. Huh? For once it works. I'm so happy. I cannot do that straight into the AC here because otherwise, for real, I will be electrocuted. So I don't want that. Now, the peak voltage is about 6 volts. So that's how a transformer works. And I'm surprised. Oh, I touch also. No, I don't know how make it work again. It's fine. So those little guides, yeah, it used to be. I don't know if you remember Radio Shack. Okay, that was amazing. Radio Shack. Actually, it was a shack. Radio Shack. So it was back then when people were playing with electronics, they will go to Radio Shack and buy all their electronic components. And then things started to be sold from China, so people didn't get into making stuff themselves. So then Radio Shack turned into selling phones and things like this. They went bankrupt, so I don't know if they recover from their bankruptcy. But before they went bankrupt, you could buy those transformers for people who wanted to build their own desktop. Okay, so these transformers are amazing. You see, I can connect that to extensions. Of course, you don't want to do that, and you go from 120 volt to 6 volt. Isn't that cool? You use that for inside your desktop. For those who are collecting Bitcoin, for example, so you can play with you can build your own computer. Who is in Bitcoin? No, some people have those crazy computer and they're collecting them. You're not going to tell me, of course, right? Hi guys, so here I did it, but that way it works, right? So I want to show you. So on one side, I'm gonna have the power supply, and on the other side, I'm gonna see if I can induce an EMF. And I close it. Poof, it works. You see? Oh, it's even better. Milliamps. So I will upload the video in YouTube. Okay, so anyway, that's the idea behind a transformer. So here you're going to connect to a AC power supply. It's going to produce a magnetic field. That magnetic field will be trapped inside that core. And that magnetic field here, because it's changing with time, will induce here an EMF. And here you can have your load. Okay, so that's the idea of a transformer. So that's how a transformer works. What's the equation? You see, if you multiply the number of loops by 2, the voltage will be multiplied by 2. Do you remember what's the power? Electric power is voltage times current, right? So because you cannot have free lunch, if the voltage is multiplied by 2, what's going to happen to the current? No, because otherwise that means you have free lunch. Divided by 2. Okay? So if the number of loops is multiplied by 20, the voltage is multiplied by 20, the current will be divided by 20. Okay, because there is no free lunch. So in the old TV, you remember those old TV from your grandfather or grandmother? That was at my time. I guess I can be your grandmother. You see, those TV, they needed like 3,000 volts or at least 1,000 volts. And how much do you get from here? From the outlet? 120. Okay, so you need to have a transformer to step up the voltage. Okay, so again, here you have AC from the outlet. Okay, so the current is going to go in one direction, the other direction. So the magnetic field is going to change. It's going to flow in one direction, in the other direction, in one direction, in the other direction. So here it's going to have an EMF. You're going to induce an EMF. So let's take an example. Because the number of feed lines poking through the area is going to change with time. So let's say here you have number of loop is 5. On that side, the number of loop is 125. Let's say the voltage here, of course, it's going to be 120 volt AC. What's going to be V2? Because of that transformer. So you go from 5 loops to 125 loops, right? So how do you go from here to there? You multiply by what? How do you go from 5 to 125? So you divide. How many times 5 goes into 125? 25. So if the number of loop is multiplied by 25, then the voltage is also multiplied by 25. That's how it works. So what's going to be the voltage? 3,000 volt. Okay, and those old TV, not anymore. Okay, the new modern TV, it's fine. 120 volt is fine, but those old TV, you see, it's like a vacuum tube, and so they needed to have a very, very, very large voltage. Not so much the current. The current was small, but the voltage had to be huge, maybe up to 5,000 volt. So that's why you need to have a transformer. What about the current? What did I say about the current? So if the current here is 1 amp in this circuit here, how much is going to be the current here? So you multiply by 25 or you divide by 25? Okay, because you don't have free lunch, so you cannot increase both the voltage and the current. You divide, so it's going to be 1 divided by 25, and you get 0.04 amps. So 40 milliamps. Okay, why? But we're going to see that in the next example, because the input energy input has to be equals to energy output. So you have V1 I1 has to be equals to V2 I2. So what's the equation for the transformer? It's very simple. You go from 1 to 2. You go from V1 voltage in the primary, so this is called the primary coil, into the voltage in the secondary coil. Here you have N1 loop, here you have N2 loop. So you have V2 over V1 equals N2 over N1. So that's the equation for the transformer. And for the current, it's going to be the opposite. It's going to be N1 here over N2. This is called here the primary coil, And this is here the secondary code. And that will be the symbol that we are using. Okay? You can have a step up transformer or you can have a step down transformer. Okay, so for the appliances that you use at home, for your laptop, you're gonna need a step down. My computer here does not like AC. So first of all, you need to convert AC to DC. And second of all, 120 will kill it. So you need to step down to 20 volt about. Is that clear? So that's how transformer works again. And it's based on Faraday's law of induction. So if you can have tablet today, you can have like a laptop. It's thanks to Mr. Michael Faraday, who didn't go to school, basically, and taught himself everything. So anyway, here you have an AC power supply. Okay, so that means the current is going to flow in one direction, in the other direction, in one direction, in the other direction. So the magnetic field will be trapped inside that core and it will flow in one direction, in the other direction. So because the magnetic field is going to change, okay, the field lines, the number of field lines poking through here, this area is going to change, you induce an EMF. Isn't that amazing, simple, and beautiful? Right? And even if you're not doing physics, you know, it's transformers are everywhere. So at the time in 19th century, you always have the difference between the scientists like Tesla, for example, or Michael Faraday, and then you have the engineers that will improve. Okay, so once it was understood how you can induce an higher voltage, okay, how you can induce a very large voltage, okay, just by increasing the number of coil, they started to think about all kind of applications so they could make money. So one idea was used in medicine. Sometimes you should not believe whatever they say, but they started, you see, to step up the voltage here. And I don't know, they will say that it will cure you. Although we do use electricity for therapy, right? But maybe it's exaggerated. I don't know if you can, if I have an issue here, you can break your thing. But you see, it's started to have a lot of commercial application. So beware of the expert, so-called expert. Money, follow the money. Okay, so why don't you try this one? So we went over the hill, okay? That was the most difficult concept to explain because actually in reality you have a lot of math behind it. Okay, so now I'm gonna let you think about that. You can help each other. So I have extended the test up to 11:59 at night. I think it opened at 8 p.m. So I'm hoping that everyone can take it. Yeah. Is there a time limit or is it like no, it's okay. So the test should be no more than 1 hour, should take you 1 hour. But you can take as much time as you want. So you can start your test, go for a snack, go back. It won't close on you. Take your dog for a walk, come back. Yeah. No, it won't. Yeah, it won't close. It's easier, and it's not proctor either. It doesn't mean that you have to use collaborative learning, right? Step down. So primary, so you go from 1 to 2. Primary, but you cannot see your answer, so make sure you think twice, okay? There is only one attempt, so think wisely, don't rush. So you have number of turns 330, and here you have 25, so that will be N1, and that's going to be N2. The plug connects the primary coil to a 120 volt wall socket. So here you have 120 volt AC. I think so. Yes, you're right. You can do cross multiplication because it's going to be a proportion. So yes, you're right. Actually, it will be smart to do that. What you want to make sure that if the number of loops decreases, the voltage has to decrease. So I guess you can do 120 times 25 divided by 330, or you try to see from 330 to 25 by how much you divide, right? But you can do cross multiply divide. So when you do cross multiply divide, it's only working with the voltage. It doesn't work for, does it? Okay, let's see. But yes, so in that case, yes, you can do cross multiply divide. You want to make sure it's going to go down. So do you all do that? Or you can say N2 over N1 equals V2 over V1. So yes, you can do cross multiply. 9 volt. Do you all get that? Right? You use this equation, it has to be a step down. But for the current, it says here, there is a current in the primary coil. So here. So what's going to happen to the current? So here we cannot use cross multiply with this because the current has to go what? If the voltage goes down, the current has to go up. So if the voltage is divided by 13.2, the current will be multiplied by 13.2. So for the voltage is the opposite, is like inversely proportional. This is the current here. Okay, so the current has to go up, which is 11 amp. Is that right? Did you all get that? Hello? Okay, it's not that hard, yes? If the number of loops is multiplied by 13.2, the voltage is multiplied by 13.2, the current will be divided by, so if the number of loops is divided, so the voltage is divided and the current is multiplied. Yes? So that means that if you have your transformer, so it's made of soft iron here, okay? So on one side, I'm gonna have a lot of loop, 330 loop here, and that's gonna be connected to my outlet with 120 volt AC. So you see what's going to happen? You're going to make a magnetic field that will be trapped inside the core, like, you know, like an electromagnet. So it's trapped, okay? And it will oscillate back and forth. It's going to change with time. So on the other side, you're going to have less loop. You have 25 loops, so less of them, 25. And what do we get here? We can connect that to a voltmeter here. So you still got AC, and the RMS will be 9 volt AC. Or you can connect that to a light bulb, for example, or something like that. Is that clear? Now the current is flowing. Here, the current is going to flow back and forth. The current here is 0.83 amps. So the current there would be 11 amp. And it's AC current, okay? It's going to flow back and forth. Is that clear? So remember, if you want to make for extra credit, you remember the electromagnet. You can take a screwdriver like this, and you wrap here with this wire has to be insulated. So you connect that, for example, to a 9-volt battery. My point is that the magnetic field here, it's going to be trapped inside, okay? It doesn't escape because this is called the core, so soft iron, it will trap the magnetic field. So that way, same way here, this here will trap the magnetic field inside. And maybe that's north, that will be south. So remember how you do that, okay? You take your right hand. So if the current is flowing this way, that will be the north here, and that will be the south. Is that clear? Yes.
For test 3, let's say the current was going counterclockwise and your thumb was pointing towards the correct north. But if you ask the direction of the magnetic field, it would be away.
No. What do you mean? If
it was counterclockwise, the current.
What do you mean? Let's go back to my thing here. Like this. You see, it's a coil. Okay, so your fingers, this one goes around the coil here. The thumb will be the magnetic field. So that means that's going to be the north. Yes, that's going to be the north, and that will be the south. So it means your coil is behaving like a bar magnet. Okay, that shows you the magnetic field. But you see, magnetic field always goes from north into the south, back to north, right? So the magnetic field shows you here which way it wants to flow. It wants to flow this way. So that will be your north. Your thumb is the north. And here, the bottom of your hand will be the south. And if you have a loop of current here inside the magnetic field, it always wants to orient itself such as it will align itself with the magnetic field. So that will be the lower state of energy, and that will be the higher state of energy. Okay, that's a MRI. That's how MRI works. So a loop of a coil, okay, will behave like a bar magnet. The thumb will show you the north, and here it will be the south. Is that clear? It's the last minute thing. Oh no, I'm not done with that. Okay, can we find the power? Okay, so that will be the energy consumed here. Okay, you get energy from the power supply. So the energy consumed will be equals to V1I1 Okay, so that's going to be equals to, what's going to be the power? So it's going to be 120 times 0.83. So what do you get? About 99 watts, 0.6 watt. On the other side, that will be the power output, okay, that you get, okay, how much energy produced per second on the other side, which is V2I2, which is 9 times 11. It's not really 11. I'm missing some decimal, but you should see it's also going to be about 99.6 watt. So whatever energy is fed in will be equals to the energy output. Okay? What comes in has to come out. The symbol for that will be the primary coil, the core in between, and then the secondary. So you have AC here and you have AC there. That will be the symbol for a transformer. Is that clear? Okay, we survived. That comes also from your book, Johnson and Cutnell. And we are almost done with that. That was the most challenging.